Hi, my name is Joe Sandoval, and this is my senior project. So my senior project is the electrical side of the characterization of the effect of electromagnetic fields on safety and quality of low moisture foods, CP Connect funded research project. It is an interdisciplinary project examining the effect and effectiveness of radiofrequency heating on the safety and quality of foods with low moisture contents. Uh, it's actually best to think about the project almost as you might a microwave. A microwave that's extremely high powered, heating a brick to 100 degrees C. To talk more about what the project entails, first I need to describe what a low moisture food is. A low moisture food uh, should be considered also in the context of a microwave, where a microwave operates by exciting water molecules at their resonant frequency and using dipole moments to cook food via friction. A low moisture food has very little active water. That refers to water accessible to microbial and organic activities. These are things like flour, wheat grain, protein powder that are hardy and hard to spoil, but also very hard to sanitize. Uh, Oftentimes, these are long carbohydrate chains, like the ones pictured to the right, uh, and they contain very few dipoles. Occasionally, you might have dipole moments at the ends of the chains, but they're so few and far between that we actually consider low moisture foods an electrical brick for all intents and purposes. So, in order to actually accomplish sanitization, what's often used is a technique called dielectric heating. Dielectric heating is at the heart of RF heating and takes advantage of material complex permittivity, a material property derived from impedance. The power absorbed by the material is what actually heats it up. Power absorbed by the material under test as a function of frequency, complex permittivity, dielectric loss angle, and electric field strength. In the model to the right, the material is being exposed by an electromagnetic field being passed through via a metal plate at the top to a ground plate on the bottom, as in a capacitor model. In industry, dielectric heating is typically done using industrial-sized devices designed to handle a pallet's worth of food at a time. The goal of this project is to miniaturize RF heating for consumer use, in essence to create a design prototype that is relatively compact, simple to use, and non-hazardous to operate. Prior to the COVID-19 crisis, the original plan was to develop a functional prototype. However, as we are no longer able to access engineering labs or facilities, the project is now exclusively simulation-based, with the goal being to create simulations of design systems. The prototype device is a three-stage system, beginning with a complete off-the-shelf DC supply able to provide 24 volts at 15 amps. That is fed into a flyback DC-DC converter, which upconverts the 24 volt supply to approximately 280 volts DC at 1 amp. That is fed into a power MOSFET square wave inverter, which converts our DC signal into a 13.56 megahertz periodic waveform, which is then fed into an RF exposure chamber where material is loaded and ultimately exposed. All system activities are controlled by a central system controller, which is external to each of the units. First system I'd like to talk about in some detail is the high voltage flyback DC-DC converter. This is the first stage and one of the more important stages, as this provides the system a reliable source of energy. It is primarily comprised of the high voltage low noise regulator, taking the 24 volt DC signal and upconverting it via the use of a flyback transformer into the desired high voltage DC signal. There are two pertinent control systems. each powered by a 5-volt DC regulator, a charge enable circuit that enables or disables up conversion by the high voltage low noise regulator, and a relay control circuit which directs the energy handled by this stage either to the next stage or through a high voltage discharge resistor. Actual schematic drawings can be seen here with each of the pertinent components singled out, with a LT-SPICE simulation of the circuit as shown on screen. The high voltage DC-DC converter was able to have a board designed. I designed a board for that just before the COVID-19 crisis made manufacture near impossible. However, it is hoped that when this project is picked up by later researchers, that the design might be implemented in a physical form. Next, we have the power MOSFET square wave inverter. It is ultimately a full bridge square wave inverter designed to accept a 280 volt DC signal and output approximately 280 volts peak to peak AC 13.56 megahertz 50% duty cycle periodic waveform. This will be fed into the RF exposure chamber. While the base schematic is of a full bridge inverter, the control circuitry for each of the control signals is actually quite involved, requiring a stable 13.56 megahertz and approximately 6.7 megahertz periodic waveforms provided to switch on and off each of the control each of the MOSFETs in the full bridge rectifier at a very specific interval. And finally, we have the RF exposure chamber. The RF exposure chamber is modeled after a parallel plate capacitor, where coaxial cables bring in and remove current from the chamber itself. The top plate is energized directly from the previous stage with our 280 volts peak to peak 13.56 megahertz periodic waveform, and a second conductor connected to the bottom plate removes current and returns it to the system ground plane. Of note is the copper cage surrounding the unit. This is intended as a safety measure to ensure that any escaping electromagnetic fields are not an imminent risk to the operator. It's now seen on screen are ANSYS HFSS simulations of said chamber design, with each component of the chamber design scoped out.